So Matt, what does MEG stand for and what is an MEG scanner?
So MEG stands for magnetoencephalography, and what we're trying to do is measure brain function. So what we do is we put very, very sensitive magnetic field detectors around the head. So when your brain starts doing something, there are electrical currents that flow through assemblies of neurons. Just like all currents, those currents generate magnetic fields, and those magnetic fields pass straight through the skull, and they exist outside the head. And our sensors measure those magnetic fields. So by measuring those magnetic fields, we can then infer what the currents were, and in that way we infer brain activity.
What are some of the problems with existing MEG technologies?
Conventional MEG technology uses superconducting quantum interference devices, or SQUIDs. And that's because they're the only sensors that are sensitive enough, or they were the only sensors that are sensitive enough to detect these very, very small magnetic fields. So these magnetic fields are tiny, about 1 billion times smaller than the Earth's magnetic field. So we need something that's very, very sensitive. Now, to get that sensitivity, what you have to do is make them very cold. So they exist at minus 269 degrees. And that gives you a lot of limitations. So first of all, they have to be a long way away from the head with a gap, an insulating gap, a vacuum, to stop the cold getting to your head. The further away we move them, the less sensitive they are to what's going on in your brain. The second limitation is because they have to exist in this vacuum, they're fixed in space, and it's a one-size-fits-all machine. The next problem is if you move relative to those sensors, then that means that we can no longer see where the signal's coming from because your head is moving inside the helmet. And of course, trying to keep children still for a long period of time is almost impossible. And the final limitation is they are very, very expensive. Not only to buy because of all of the equipment that was required for the cryogenics, but also they're expensive to maintain.
So what about these new sensors that you've been developing, and how do they solve some of these problems?
So the new sensors that we use are called optically pumped magnetometers, and they exploit quantum physics, quantum mechanics, to measure magnetic fields. The biggest benefit of them is they don't need cryogenic cooling, and they're very small. They're about the size of a Lego brick. So what you can do is you can bring them very, very close to the head, so we avoid this problem of having to have this large insulating gap. We get them closer to the head. That means they pick up more signal, much more sensitive. They're also quite light, so you can sort of mount them in a helmet, and you can move your head, and as you move your head, the sensors move with you. That means that if you're imaging, say, a child who can't keep still, or an adult who can't keep still, because the sensors move with the head, they can move freely. So we're getting increased sensitivity, we're getting them closer to the head. It's adaptable, because if you've got a child with a small head, you just put them in a smaller hat. And because it moves with the head, it allows free movement during a scan.
So how are these technologies, these systems, changing people's lives today?
So these systems are being installed around the world. And really being placed into the hands of the neuroscientists who can best exploit them. And so we are doing research studies on disorders like autism, epilepsy, dementia. But at the minute they are limited to research. Now what we'd really like is medical device approval, but as you can imagine, that quite rightly requires testing, a lot of reproducibility, reliability, and we're not there yet. But the big hope is that in a year or two's time we get medical device approval. Now, in epilepsy, around a third of epilepsy cases can't be treated by drugs, and those patients become candidates for brain surgery. So what we hope is that this technology can be used, just a set of sensors very close to the head. We can map which parts of the brain are generating epilepsy. And that becomes useful information for the neurosurgeons then to say, okay, this is where we target for our surgery. Even if we could just give the invasive measures a better target, that would significantly, it would revolutionise actually the epilepsy surgery pathway.
What's the thing that you're most excited about?
For me personally, I've sort of always said if something that our group has done ultimately can lead to one patient having a better life than they would have done if we hadn't developed that technology, I'll consider that a job well done, I think.